Right now, a machine drifting more than 1 million miles away from Earth is quietly reshaping what we thought we understood about the universe. For decades, scientists believed the cosmos was unimaginably vast, yet still something we could measure, extending roughly 14 billion light-years in every direction. Then, the James Webb Space Telescope turned its mirrors toward what appeared to be empty darkness, and that confidence began to fade. Webb revealed galaxies forming far earlier than expected, black holes growing faster than current theories can fully explain, and structures emerging at a time when the universe should still have been in its earliest stages. But the most unsettling part is not simply how far Webb can see. It is what these discoveries imply about the true scale of reality, and how much of the universe may always remain beyond our reach. If you're ready, let's explore what the James Webb Space Telescope has revealed this time. To understand what the James Webb Space Telescope is truly revealing, we first need to reconsider a simple but deeply misleading idea about the universe. The idea that space is something we simply look across, like a landscape stretching into the distance. In reality, the universe does not behave like a landscape. In the cosmos, distance is not just distant, it is also time. Light travels at a constant speed of about 300,000 kilometers per second, the fastest speed that exists. Fast enough to circle the Earth more than 7 times in a single second. At human scales, that speed feels almost instantaneous, so fast that our senses treat light as if it arrives the very moment it leaves its source. But across the vast distances of the universe, even light cannot remove delay. The moment light leaves an object, its journey begins. When you look across a room, you are seeing the past by a few billionths of a second, a delay so small that the brain completely ignores it. When you look at a distant building, that delay stretches slightly longer into millionths of a second. And even then, it remains too small to matter in daily life. But the universe operates on scales far beyond anything we experience day to day. When you look at the moon, the light reaching your eyes left its surface about 2 seconds earlier. The moon you see in the sky is not the moon as it exists right now, but as it was 2 seconds in the past. When you look at the sun, the delay increases to roughly 8 minutes. Sunlight must travel across about 93 million miles before reaching Earth. If the sun were to suddenly disappear at this very moment, the sky would not go dark immediately. For another 8 minutes, sunlight would continue to arrive, carrying information from a star that no longer exists. Beyond that, the delays grow rapidly. The nearest star beyond our sun appears to us as it was more than 4 years ago. When astronomers observed the center of the Milky Way, the light entering their instruments began its journey roughly 26,000 years ago, long before the earliest human civilizations appeared. And when telescopes observed the Andromeda galaxy, the light we detect today left its stars about 2 million years ago. Long before recorded history, and long before modern humans spread across the planet. The night sky, in other words, is not a live view of the universe. It is a record of the past. Every star, every galaxy, every faint point of light carries a timestamp from the moment its light began crossing the cosmos. Each photon arriving at Earth today has been traveling through space for years, centuries, or even billions of years. The farther away an object is, the older the story carried by its light. But the universe does not preserve these messages unchained. Space itself is expanding. And while that idea may sound abstract, it has profound consequences for how we observe the cosmos. Galaxies are not simply drifting away from one another through empty space. Instead, The fabric of space itself is stretching, slowly increasing the distance between galaxies over time. And, as space stretches, the light moving through it stretches as well. As light crosses billions of light years of expanding space, its wavelength gradually becomes longer. Energetic blue light shifts toward red, and eventually moves into infrared wavelengths that are invisible to the human eye. Astronomers refer to this effect as redshift. But redshift is more than just a change in color. It acts as a kind of cosmic timestamp. The more that light has been stretched, the longer it has been traveling, and the earlier in the universe's history it must have been emitted. Distance and time become inseparable. To look farther into space is to look deeper into the past. For decades, astronomers relied on telescopes designed mainly to observe visible light. The narrow range of wavelengths that human eyes can detect, instruments such as the Hubble Space Telescope, transformed our understanding of the universe, revealing detailed views of galaxies, star-forming regions, and nebulae scattered across nearby space. But as scientists tried to push their observations further back toward the beginning of cosmic history, the universe began to appear unexpectedly empty. Not because it was truly empty, but because its light had changed. As light from the earliest galaxies traveled through the expanding universe, its wavelength stretched beyond the visible spectrum. By the time that light finally reached Earth, much of it had shifted into infrared wavelengths that earlier telescopes were not designed to detect. To those instruments, large portions of the early universe appeared dark, but that darkness was misleading. It was not emptiness. It was simply light that had moved beyond our ability to see. The James Webb Space Telescope was built specifically to detect this hidden light rather than focusing on visible wavelength. Webb is designed to observe infrared radiation, allowing it to capture signals from galaxies whose light has been traveling for more than 13 billion years. Its mirror spans more than 6 meters across and is coated with a thin layer of gold, chosen because gold reflects infrared light with exceptional efficiency. This design allows Webb to capture incredibly faint signals that earlier telescopes simply could not detect. But observing infrared light comes with a major challenge. Infrared radiation is closely linked to heat, and any warm object emits it, including the telescope itself. If Webb were warm, it would glow in the very wavelengths it is trying to observe, overwhelming the delicate signals arriving from distant galaxies. To prevent this, Webb must remain extremely cold, a giant 5-layer sunshield, roughly the size of a tennis court, blocks heat and light from the sun, the Earth, and the Moon. On the shaded side of that shield, the telescope cools to temperatures of around -230 degrees Celsius. At such low temperatures, Webb becomes quiet enough to detect even the faintest traces of ancient light. The telescope operates nearly 1.5 million kilometers from Earth, positioned at a stable gravitational balance point known as Lagrange Point 2. From this distant location, shielded from heat and interference, Webb can stare into deep space for long, uninterrupted periods. When it turns its mirrors toward a region of sky that appears completely black to our eyes, it is not searching for nothing. It is waiting for photons that began their journey when the universe was still young. These photons do not arrive all at once. Sometimes they reach the telescope one by one, carrying faint signals from galaxies whose light has been traveling for billions of years. Webb may observe the same patch of sky for hours, or even days, slowly collecting these ancient photons until an image begins to take shape. And what emerges from that darkness is not silence. Galaxies begin to appear where emptiness once seemed to exist. Systems already forming stars, already building structure, already evolving in ways that challenge earlier expectations. The early universe does not appear fragile or incomplete. It appears active. Each image Webb produces is not a simple snapshot. It is a mosaic assembled from ancient light, with every photon in the frame having traveled across billions of years before reaching the telescope. By the time that light arrives, the stars that produced it may already be gone, and the galaxies that emitted it may have changed in profound ways. What we see is not the universe as it exists today, but the universe as it once was. For this reason, astronomers often describe telescopes like Webb not simply as tools for looking far into space, but as instruments for looking back through time. Nearby galaxies reveal a universe closer to the present moment. More distant galaxies show earlier chapters of cosmic history. And the most distant objects ever detected reveal the universe when it was still very young. But even the remarkable reach of the James Webb Space Telescope has its limits. There is a boundary beyond which no telescope can see. Not because of technological constraints, but because of the fundamental laws of the universe itself. Light has had only a finite amount of time to travel since the beginning of the cosmos, which means there is a maximum distance from which light could ever reach us. Astronomers call this limit the observable universe. It is not the edge of space, but the edge of information beyond that boundary. The universe continues to exist. Galaxies continue to form and evolve. Stars ignite and collapse, and black holes merge in regions whose light will never reach Earth, simply because the expansion of space prevents those signals from crossing the vast distance between us. The James Webb Space Telescope has not revealed the edge of everything that exists. Instead, it has shown us how much of reality lies beyond what we can ever observe. And as Webb moves closer to that boundary, detecting galaxies earlier and earlier in cosmic history, a deeper realization begins to emerge. If the universe already appears this rich and structured at the very limits of what we can see, then the true scale of everything beyond that horizon may be far greater than we once imagined. For many years, astronomers believed they had a fairly clear picture of how the early universe unfolded. The Big Bang filled space with hot, dense matter, which then expanded and gradually cooled. Gravity began working quietly in the background, slowly pulling material together. Over time, small irregularities in that nearly uniform distribution of matter grew stronger, drawing gas inward and giving rise to the first stars and galaxies. In this view, cosmic evolution was expected to be gradual. The earliest galaxies should have been small and faint, fragile collections of stars only just beginning to take shape. Gas needed time to cool and collapse. Dark matter halos needed time to grow large enough to capture ordinary matter. And the formation of stars themselves required millions of years. Even after the first stars appeared, building large galaxies was thought to be a slow process, involving repeated mergers and the steady accumulation of material. The early universe, according to these expectations, should have been relatively quiet, not empty, but sparse. When the James Webb Space Telescope began observing extremely distant regions of space, astronomers expected to find only a few primitive galaxies scattered across a young cosmos that was still forming its first structures. Instead, Webb found something very different. Bright galaxies appeared again and again in periods that should have contained very few of them. These were not faint sparks barely holding together. Many were already forming stars at remarkable rates, producing vast amounts of light. The surprise was not just a single unusual object. It was the pattern. Again and again, Webb detected galaxies within the universe's first few 100 million years that were far brighter and more massive than theoretical models had predicted. Some of these systems already contained hundreds of millions, or even billions, of solar masses in stars. According to long-established models of galaxy formation, structures of that size should have taken much longer to build. Gravity is powerful, but it is not instantaneous. Gas clouds do not collapse the moment gravity begins pulling on them. They must first lose energy and cool before they can contract efficiently. Dark matter halos must grow large enough to trap ordinary matter. Stars must form, evolve, and enrich their surroundings with heavier elements before galaxies can develop complex structures. Each of these steps requires time. And yet, when Webb looked into the early universe, many of those steps appear to have already taken place. Even more intriguing is the chemical composition of some of these young galaxies. Webb has detected elements such as carbon and oxygen within them, elements that were not created during the Big Bang. They are formed inside stars, and only released into space when those stars reach the end of their lives. Often in powerful supernova explosions, their presence in these early galaxies suggests that at least one generation of stars had already formed, lived out their life cycle, and ended in explosive deaths before the galaxies we now observe had even taken shape. The cosmic timeline, in a sense, appears compressed. Events that scientists once believed required hundreds of millions of years may have unfolded far more quickly. To understand why this is so puzzling, it helps to imagine building a city. You cannot raise skyscrapers before roads exist, and you cannot pour concrete before producing steel. Each stage depends on the one before it. The early universe was expected to be laying its foundation. Instead, Webb seems to reveal structures already rising. This growing mismatch between theoretical expectations and observation has become informally known among researchers as the problem of too much light too early. When astronomers estimated how much light galaxies should produce during the universe's first billion years, their models consistently predicted far less brightness than what Webb was observing. And the difference was not subtle. In some cases, the galaxies being observed appeared several times brighter than expected. When faced with such a discrepancy, scientists naturally look first for simpler explanations. Perhaps the measurements were misleading. Perhaps dust within these galaxies was influencing the observations, or gravitational lensing from galaxies in between was magnifying distant systems, making them appear brighter than they truly are. Another possibility involved rapidly feeding black holes at the centers of these galaxies. As matter spirals into a black hole, it can release enormous amounts of energy, producing intense light that could make a galaxy appear larger or more luminous than it actually is. These possibilities were carefully examined. In some cases, actively feeding black holes did contribute additional brightness. Accounting for their influence helped reduce some of the most extreme mass estimates for early galaxies, but the overall pattern remained. Even after these corrections were applied, the early universe still appeared to contain far more bright galaxies than standard models had predicted. The tension eased slightly, but it did not disappear. Webb repeated these observations across different regions of the sky, using multiple instruments and wavelengths, and the results remained consistent. The early universe appeared unexpectedly active, with star formation occurring at a much faster pace than anticipated. This forced astronomers to reconsider a key assumption: how efficiently the universe can convert gas into stars. In the modern universe, star formation is surprisingly inefficient. Most of the gas within galaxies never becomes star. It is heated by radiation, stirred by turbulence, or pushed away by stellar winds and supernova explosions. Only a small fraction eventually collapses to form new stars. The early universe may have behaved very differently. One possibility is that conditions were simply denser. In its early stages, galaxies were closer together, and gas clouds were packed far more tightly than they are today. Frequent collisions between galaxies may have compressed this gas, triggering bursts of rapid star formation. Another possibility lies in the composition of the earliest gas cloud. The first stars formed from almost pure hydrogen and helium, without the heavier elements that influence how gas cools and collapses. Under these simpler conditions, star formation may have proceeded in ways that no longer occur in the modern universe. Mergers likely played an important role as well. When galaxies collide, gas is driven inward toward their centers, becoming compressed and heated. This process can trigger intense waves of star formation, producing large numbers of stars over relatively short periods of time. Each of these explanations may account for part of the puzzle, but none of them fully resolves it. Adding to the mystery, Webb has also detected evidence of supermassive black holes existing far earlier in cosmic history than expected. Some of these black holes appear to have formed when the universe was less than 500 million years old. Yet they already contain millions, or even billions, of times the mass of the Sun. According to conventional models, black holes begin as the collapsed remnants of massive stars, typically containing only a few tens of solar masses. Growing them into supermassive objects should require long periods of steady accretion and repeated mergers. And yet, Webb continues to detect massive black holes at remarkably early stages of the universe. This has led astronomers to consider possibilities that once seemed unlikely. Perhaps the earliest stars were far more massive than those we see today, collapsing directly into large black holes. Perhaps enormous clouds of gas collapse straight into black holes without forming stars first. Or perhaps the early universe contained conditions that allowed black holes to grow much faster than we currently understand. For now, none of these explanations has been confirmed, but none can be ruled out either. What makes these discoveries especially important is that the earliest galaxies shaped everything that followed. Their radiation changed the state of the surrounding gas, and their supernova explosions spread heavy elements throughout space. Their gravity also helped build the large-scale structures that would later evolve into galaxy clusters and vast cosmic filaments. If galaxies formed earlier and more rapidly than expected, then the entire timeline of cosmic evolution may need to be reconsidered. The universe may have assembled its first major structures far sooner than scientists once believed, and as the James Webb Space Telescope continues to look deeper into space and further back in time, the same pattern continues to appear. The early universe was not slow or hesitant. It was already active. Stars were forming, galaxies were growing, and black holes were already accumulating mass. All within a cosmic era that was once expected to be nearly empty. The universe did not wait. It began building itself almost immediately. For much of modern astronomy, scientists believed they had reached a fairly solid answer to one of the biggest questions imaginable. How many galaxies exist in the universe? The method seemed straightforward. Even if the scale itself was extraordinary, astronomers would point a powerful telescope at a very small patch of sky that appeared almost completely empty. They would then count every galaxy visible within that tiny region and use that number to estimate how many similar regions exist across the entire sky. If you know how many galaxies occupy a small sample of the universe, you can scale that number up to approximate the whole. When the Hubble Space Telescope carried out one of the deepest observations ever attempted, the results surprised even the scientists involved. In a tiny patch of sky no larger than a grain of sand held at arm's length, Hubble revealed nearly 10,000 galaxies, The image became known as the Hubble Ultra Deep Field. Before that observation, many astronomers suspected that distant space would become increasingly empty as telescopes looked farther outward. Instead, Hubble revealed the opposite. The deeper it looked, the more galaxies appeared. From those observations, astronomers estimated that the observable universe contained roughly 100 to 200 billion galaxies. The number was almost impossible to fully grasp. Yet for many years, it remained the best estimate available. Then the James Webb Space Telescope began observing the same darkness, where earlier images showed scattered islands of light separated by vast black space. Webb revealed additional layers of structure. Regions that once seemed empty began to glow faintly in infrared wavelengths. Galaxies that had been invisible to previous instruments slowly emerged from the background. This was not because earlier telescopes were wrong, but because they were observing the wrong part of the spectrum. As light from distant galaxies travels across billions of years of cosmic expansion, its wavelength stretches. Light that originally existed in visible wavelengths gradually shifts into infrared. By the time it finally reaches Earth, much of it has moved beyond the range that older telescopes were designed to detect. The galaxies were always there. Their light had simply drifted beyond the limits of our vision. The James Webb Space Telescope was built specifically to follow this stretched light. Its instruments are designed to detect infrared radiation with extraordinary sensitivity, allowing it to reveal galaxies that earlier telescopes could not see. When Webb began conducting its deep field observations, it once again pointed toward regions of sky that appeared nearly empty. But instead of finding only a few distant objects, Webb uncovered dense layers of galaxies spread across cosmic time. In some deep observations, hundreds of thousands of galaxies appear within a relatively small patch of sky. Each of these galaxies contains enormous numbers of stars, some with billions, others with trillions. Many contain clouds of gas and dust where new stars are still forming, and many likely host planetary systems orbiting those stars. The universe, it turns out, is not sparsely populated with isolated galaxies drifting through empty space. It is crowded. What makes this realization even more remarkable is that Webb does not simply detect galaxies. It can also measure them by analyzing the redshift of their light. Astronomers can estimate how far away each galaxy is, and therefore how far back in time it formed. Webb can also estimate how quickly these galaxies are forming stars, and the approximate amount of mass they contain. When scientists combine all of these measurements, they begin to reconstruct the history of galaxy formation across billions of years. And when that history is pieced together, a striking pattern begins to emerge. Galaxies are not scattered randomly throughout space. They tend to gather together. On the largest scales, galaxies form vast, interconnected structures that stretch across hundreds of millions of light years. These structures resemble enormous filaments, linking galaxy clusters into long strands that span distances almost beyond comprehension. Between these filaments lie immense voids, regions of space containing very few galaxies at all. Taken together, this pattern resembles a gigantic three-dimensional web. Astronomers refer to this structure as the cosmic web. It is not accidental, but something that emerged gradually from the earliest moments of cosmic history. After the Big Bang, matter was distributed almost evenly across space. But even then, tiny variations in density were present from the very beginning. Regions that were slightly denser exerted a slightly stronger gravitational pull. Over time, matter slowly flowed toward those regions, amplifying the differences. Gravity drew material inward, forming dense filaments and clusters. while leaving behind vast regions where very little matter remained. A helpful way to picture this process is to imagine rainfall across a landscape. Water flows downhill, gathering in valleys and carving rivers through the terrain. Over time, a structured network of channels forms, while higher ground remains relatively dry. In a similar way, matter flowed through the universe under the influence of gravity, gradually forming the vast filaments and clusters that define the cosmic web. The James Webb Space Telescope is now helping astronomers map this structure with far greater clarity than ever before, because it can detect extremely distant galaxies that were previously invisible. Webb is filling in missing pieces of the cosmic map. Entire populations of faint galaxies have appeared in regions where earlier surveys saw only darkness. This matters because the distribution of galaxies is not just a visual pattern. It carries information about how the universe evolved. The way galaxies cluster together reveals how matter moved through space over billions of years, how gravity shaped large-scale structures, and how the earliest fluctuations in matter eventually grew into the vast cosmic architecture we observe today. Webb's observations show that many of these structures began forming surprisingly early. Some long filaments of galaxies already existed when the universe was only a few billion years old. In certain regions, galaxies appeared tightly grouped together, suggesting that gravity was already shaping large clusters earlier than many models had predicted. But the cosmic web is not only a network of galaxies, it is also defined by emptiness. Between its dense filaments lie enormous cosmic voids, regions where almost no galaxies exist. Some of these voids span tens or even hundreds of millions of light-years. If an observer were positioned near the center of one, they might look in every direction and see almost nothing at all. These voids are among the largest structures in the universe by volume. In other words, the universe is both crowded and empty at the same time. Dense clusters of galaxies lie along vast filaments, while enormous regions of near darkness stretch between them. And when astronomers use Webb's deep field observations to estimate how many galaxies might exist across the observable universe, the numbers become almost overwhelming. The earlier estimate of around 100 billion galaxies now appears to be only part of the story. If Webb's observations reflect the wider universe, the true number could be far greater, possibly reaching into the trillion. Each galaxy contains stars. Many of those stars host planets, and each one represents its own unfolding history across billions of years. And yet, even this immense number applies only to the portion of the universe we are able to observe. Beyond the limits of our vision, space continues. Galaxies continue. The cosmic web extends into regions whose light will never reach us. And if the universe already appears this rich within the boundaries we can see, then the true scale of what lies beyond becomes almost impossible to fully imagine. At first glance, the size of the universe might seem straightforward to estimate. The Big Bang occurred about 13.8 billion years ago. And since light travels at a constant speed, it feels natural to assume that the most distant objects we can observe should lie about 13.8 billion light-years away. In everyday terms, that reasoning seems perfectly logical, yet the real picture is far more surprising. In reality, the observable universe has a radius of about 46 billion light-years, giving it a total diameter of roughly 93 billion light-years. This is not speculation or exaggeration. It follows directly from measurements of cosmic expansion and from how ancient light travels through space. What makes this result feel so counterintuitive is that it conflicts with how we instinctively think about motion and distance. Nothing can move through space faster than the speed of light. And that rule still holds across the entire universe. No galaxy is racing through space at impossible speeds. And no signal is breaking the fundamental limits set by physics. The confusion arises because the expansion of the universe is not like objects flying outward through space, the way fragments scatter from an explosion. Instead, something far more subtle is happening. The universe expands by stretching space itself. When astronomers say that distant galaxies are moving away from us, it can sound as though those galaxies are traveling through empty space, like ships leaving a harbor. But, on large scales, that is not what is happening. Galaxies are not really moving through space in that way. Instead, the space between them is gradually expanding, increasing the distance that separates them. A useful way to picture this is to imagine small dots drawn on the surface of a balloon. As the balloon inflates, each dot moves farther away from every other dot, not because the dots themselves are sliding across the surface, but because the surface itself is stretching. Every dot sees the others drifting away. Even though none of them occupies a special center, the large-scale expansion of the universe behaves in a very similar way. When a distant galaxy emitted the light that our telescopes detect today, it was much closer to our region of space than it is now. Over the billions of years that light traveled toward Earth, the universe continued to expand, steadily increasing the distance between galaxies. By the time that light finally reached us, the galaxy that emitted it had already been carried tens of billions of light-years farther away. This is why we can observe galaxies whose light has been traveling for more than 13 billion years. Even though those galaxies are now much farther away than 13 billion light-years, the light we detect did not cross a fixed distance. Instead, it traveled through space that was continuously expanding along the way. In effect, the path the light had to cross kept increasing as the light moved forward. Early in the universe's history, the expansion rate was slower, allowing light to make steady progress across space over billions of years. However, the expansion accelerated, stretching distances faster and faster. Some photons began their journeys early enough to eventually reach us despite that expansion, while others never will. This naturally creates a boundary, but it is not a wall. And it is not an edge in the usual sense. Astronomers refer to it as the cosmic horizon, a limit marking the farthest distance from which light has had enough time to reach us since the beginning of the universe. Beyond that horizon, space continues to exist, but the light from those regions has simply not had enough time to reach us. The important point is that the cosmic horizon does not represent the edge of the universe itself. It marks only the limit of what we are able to observe from our particular position in space and time. And several lines of evidence suggest that the universe extends far beyond that boundary. When astronomers examine how galaxies are distributed across the sky, they do not see their density fading towards some distant edge. Instead, the universe appears broadly similar in every direction. The faint afterglow of the Big Bang, known as the cosmic microwave background, is also remarkably uniform across the sky, a pattern that would be extremely unlikely if space suddenly ended just beyond what we can see. All of this points to a simple, yet unsettling conclusion. The universe almost certainly extends far beyond the portion we are able to observe. Beyond the cosmic horizon, there may be galaxies, clusters, and vast structures similar to those we see nearby. And yet, the light from those regions will never reach us, because the space between us and them is expanding too quickly. No matter how powerful our telescopes become, they cannot overcome this fundamental limitation. Even more intriguing is the fact that the cosmic horizon itself is not fixed. As time passes, the observable universe slowly grows larger, because light from increasingly distant regions has had more time to reach us. In that sense, the horizon gradually expands outward. At the same time, however, cosmic expansion is accelerating, meaning the distances between galaxies are increasing faster than they once did. These two processes interact in complex ways. Some galaxies that were once invisible eventually come into view as their light finally reaches us, revealing regions of the universe that were previously hidden. At the same time, other galaxies are carried so far away by cosmic expansion that the light they emit today will never reach Earth. Over extremely long timescale, those galaxies will effectively fade from view. If the expansion of the universe continues at its current rate, observers tens of billions of years in the future may see a very different sky. Nearly every galaxy beyond our local group will have drifted past the cosmic horizon, leaving only a small cluster of nearby galaxies visible in an otherwise dark universe. From their perspective, it may appear as though the universe contains only a handful of galaxies. They may never realize that the cosmos was once filled with trillions. This idea also changes how we think about observation itself. The observable universe is not a single boundary that applies everywhere. It depends entirely on where the observer is located. An observer in a distant galaxy, billions of light years away, would see a different observable universe than we do, with some regions visible to them that will remain forever hidden from us. Every location in space effectively sits at the center of its own observable universe. There is no single viewpoint from which the entire cosmos can be seen. This is one of the reasons telescopes like the James Webb Space Telescope are so important. By detecting galaxies closer to the cosmic horizon than any instrument before it, Webb pushes our window of observation as far as the laws of physics allow, revealing structures that formed when the universe was still in its earliest stages. Yet even Webb cannot see beyond that horizon. The galaxies whose light it detects near the edge of the observable universe are not where they appear in the images we capture. Their light began its journey billions of years ago, and throughout that immense passage of time, the universe has continued to expand. The galaxies themselves may have changed dramatically since the moment that light was first emitted. What we observe, therefore, is not the present universe, but a collection of ancient signals arriving from distant moments in cosmic history. And beyond the boundary from which those signals originate lies a far larger universe that remains permanently hidden from view. The James Webb Space Telescope has not discovered an edge to the cosmos. Instead, it has revealed something far more profound. The universe may extend far beyond the limits of what any observer could ever see. For much of the 20th century, the story of the universe seemed relatively clear. The Big Bang set everything in motion. Space began expanding, and gravity slowly worked to shape the cosmos. Galaxies gathered into clusters. Stars formed within swirling clouds of gas. And the large-scale structure of the universe gradually took form. Underlying this picture was a simple assumption: gravity, the force that pulls matter together, was expected to slow the expansion of the universe over time. Since every galaxy contains enormous amounts of mass, and mass attracts other mass, astronomers assumed that the outward motion left over from the Big Bang must gradually be losing momentum. The galaxies moving apart should have been slowing down as gravity pulled them back toward one another. For decades, the central question in cosmology was not whether expansion was slowing, but how quickly. Some scientists even considered the possibility that gravity might eventually stop the expansion entirely and reverse it, causing the universe to collapse back in on itself in a distant future, sometimes referred to as the Big Crunch. Then, near the end of the 1990s, astronomers made a discovery that changed this picture completely. Two independent teams of researchers were studying distant stellar explosions known as Type 1a supernovae. These events occur when certain stars reach a critical mass and explode with extraordinary brightness. Because these explosions reach nearly the same peak luminosity each time, astronomers can use them as reliable cosmic distance markers by comparing how bright a supernova appears in the sky with how bright it is known to be. Scientists can estimate how far away it is. When that distance is compared with how quickly the host galaxy is moving away from Earth, astronomers gain insight into how the expansion of the universe has changed over time. The results were unexpected. The expansion of the universe was not slowing down. It was accelerating. Distant galaxies were farther away than they should have been if gravity alone was shaping the expansion. The deeper astronomers looked into space, the clearer this pattern became. Instead of gradually losing speed, the expansion of the universe had been increasing for billions of years. Something was pushing space apart. To account for this effect, cosmologists introduced a new concept known as dark energy. Dark energy cannot be observed directly. It does not emit light, absorb radiation, or produce signals that telescopes can detect. Instead, its existence is inferred from its influence on the expansion of the universe. Yet, despite being invisible, dark energy appears to dominate the cosmos. Current measurements suggest that roughly 68% of the universe consists of dark energy, ordinary matter, the atoms that make up stars, planets, gas clouds, and living system. Accounts for less than 5% of the total cosmic content. Most of the remaining mass exists as dark matter, another invisible component whose true nature remains one of the great mysteries of modern physics. In other words, the familiar universe of stars and galaxies represents only a small fraction of reality. What makes dark energy especially unusual is how it behaves as the universe expands. Normal matter becomes diluted as space grows larger. If the volume of the universe increases, the same amount of matter spreads out over a greater distance, reducing its overall density. Radiation behaves in a similar way, thinning out even more quickly as the universe expands. Dark energy, however, does not follow this pattern. Instead, its density appears to remain nearly constant, even as space itself continues to grow. As the universe expands, more dark energy effectively fills the additional volume. In other words, the total amount of dark energy increases along with the expansion. This creates a remarkable feedback effect. The more the universe expands, the more dark energy there is, and the stronger its influence becomes on cosmic expansion over billions of years. This process gradually shifted the balance of power in the universe. In the early cosmos, matter was dominant. Gravity shaped the formation of galaxies and clusters, pulling gas inward and building the large-scale structure that telescopes now observe. But as space expanded and matter became more diluted, dark energy began to take on a greater role. Around 5 billion years ago, dark energy became the dominant influence on cosmic expansion. From that point onward, the expansion of the universe began to accelerate. The James Webb Space Telescope does not observe dark energy directly, but its effects are visible throughout the data it collects. The vast size of the observable universe, the extreme stretching of ancient light, and the way distant galaxies recede deeper into space all reflect the influence of accelerated expansion. Without dark energy, the universe we see today would look very different. The cosmic horizon would be much closer, because expansion would have slowed more significantly over time. Many of the distant galaxies that Webb now detects would never have reached the positions where we observe them today. In a sense, dark energy has stretched the universe open. It has allowed the observable cosmos to reach the immense scale we see now. But dark energy does more than shape the present universe. It also determines its long-term future. If it continues to behave as current observations suggest, then cosmic expansion will keep accelerating indefinitely. Gravity will still hold galaxies and clusters together on local scales. But across larger distances, the separation between cosmic structures will continue to increase. Over immense spans of time, more and more galaxies will drift beyond the cosmic horizon. Trillions of years from now, observers within a galaxy like the Milky Way may look out into the sky and see only their own galaxy and a few nearby companions. The rest of the universe will have expanded so far away that its light can no longer reach them. In that distant era, the cosmos may appear almost empty, which makes our current moment in cosmic history somewhat unusual. We exist at a time when the universe is old enough for galaxies to have formed across vast distances, yet still young enough that we are able to observe many of them. Even so, the story of cosmic expansion still contains a puzzle that scientists are trying to resolve. When astronomers measure how fast the universe is expanding today, two different methods produce slightly different results. One approach looks deep into the early universe by studying the cosmic microwave background. This is the faint radiation left over from a time when the universe was only about 380,000 years old. Patterns within that ancient light allow scientists to calculate an expansion rate of roughly 42 miles per second for every megaparsec of distance. A second method focuses on the nearby universe. Astronomers measure distances to galaxies using Cepheid variable stars and Type 1a supernovae. Then compare those distances with how quickly those galaxies are moving away from us. This second method consistently gives a higher expansion rate, around 73 kilometers per second per megaparsec. Both approaches rely on extremely precise observations and have been tested repeatedly using independent data. Yet, even after years of careful analysis, the two results still do not agree. This disagreement is known as the Hubble tension. It has become one of the most intriguing problems in modern cosmology. If both measurements are correct, then our current understanding of how the universe expands may be incomplete. The James Webb Space Telescope was expected to help clarify this by improving the accuracy of distance measurements in the nearby universe. Instead, Webb's observations have strengthened the evidence for the higher expansion rate, rather than resolving the discrepancy. The new data has made the tension even more difficult to ignore. This leaves cosmologists facing several possibilities. There may be subtle errors within one of the measurement techniques, or there may be new physics influencing cosmic expansion in ways that are not yet fully understood. Whatever the explanation turns out to be, the discovery of dark energy has already transformed our understanding of the universe. It revealed that the universe is not simply expanding, it is accelerating. Dark energy stretches space itself, steadily pushing distant galaxies farther apart and shaping the cosmic horizon that defines what we can observe. Yet dark energy is only one part of the invisible forces that govern the cosmos. While dark energy drives expansion on the largest scales, something else must pull matter together on smaller scales, allowing galaxies, clusters, and the vast structures revealed by the James Webb Space Telescope to form at all. That unseen influence is known as dark matter, and it provides the hidden framework that holds the universe together. If dark energy determines how the universe expands, dark matter plays a key role in how it holds together. Without this second component, the universe revealed by modern telescopes would not exist in anything like its current form. Galaxies would struggle to form, clusters would disperse, and the large-scale structure stretching across the cosmos would never have emerged. This hidden component, dark matter, does not emit light, reflect light, or absorb radiation in any way that telescopes can directly detect. In that sense, it is completely invisible, and yet, its gravitational influence is unmistakable, and the amount of it present in the universe appears to be immense. Current measurements suggest that around 85% of all matter in the universe is dark matter. Everything familiar. Stars, planets, clouds of gas, dust, and even the atoms within our own bodies makes up only a small fraction of the total mass. What we see is only the illuminated surface of a much larger structure. The first signs that something unseen was influencing galaxies appeared nearly a century ago. Astronomers studying the rotation of spiral galaxies noticed that stars in their outer regions were moving far faster than expected. According to the known laws of gravity, those stars should have been flung outward into intergalactic space if only visible matter were holding the galaxies together. But they were not escaping. Instead, the outer stars continued orbiting at high speeds, as if they were embedded within vast halos of unseen mass. The visible stars and gas accounted for only a small portion of the total gravitational structure. Something invisible was providing additional gravity. As observations improved over the decades, similar evidence began to appear on larger scales. Entire clusters of galaxies showed far more gravitational pull than could be explained by the matter astronomers could actually see. When scientists examined how galaxies moved within these clusters, their motion revealed that enormous amounts of hidden mass must be present. Another strong line of evidence comes from a phenomenon known as gravitational lensing. According to Einstein's theory of general relativity, massive objects can bend the path of light passing near them. When astronomers observe distant galaxies through large clusters of foreground galaxies, the background light appears distorted and magnified. By measuring these distortions, scientists can estimate how much mass is present within the cluster. Again and again, the results show that visible matter alone is not enough. Most of the mass must be invisible dark matter. Although it cannot be observed directly, its behavior appears to follow relatively simple rules. Unlike ordinary matter, which collides, heats up, and emits radiation, dark matter seems to interact mainly through gravity. It moves through space without friction and does not lose energy in the way normal gas does. This difference had profound consequences during the early history of the universe. Shortly after the Big Bang, matter was spread almost evenly across space, with tiny variations in density throughout the young cosmos. Dark matter responded to those variations first, because it did not interact with radiation. It was free to begin clumping together under the influence of gravity, while ordinary matter remained too hot and energetic to collapse. Over time, these clumps grew into massive halos of dark matter, invisible structure, hundreds of thousands of light years across, began forming long before the first stars ignited. As the universe cooled, ordinary matter gradually fell into these dark matter wells. Gas gathered within them, became compressed, and eventually heated enough to ignite nuclear fusion. The first stars were born. Those stars later gathered into galaxies, but the locations where galaxies formed were not random. They formed precisely where dark matter had already created the deepest gravitational wells. In this way, the visible universe followed an unseen blueprint. Dark matter shaped the structure, and ordinary matter illuminated it. This process produced one of the most remarkable patterns in nature, the cosmic web. On the largest scales, galaxies are arranged along enormous filaments that stretch across tens and hundreds of millions of light years. These filaments intersect at dense nodes where galaxy clusters form. while vast empty regions known as cosmic voids fill the spaces between them. The result resembles a three-dimensional network woven across the entire observable universe. For many years, this cosmic web existed mainly in computer simulations. Cosmologists used powerful supercomputers to model how dark matter should behave over billions of years. And the results consistently produced a filament-like structure that closely matched what astronomers observed. The James Webb Space Telescope is now helping to confirm these predictions with unprecedented detail by detecting hundreds of thousands of galaxies and measuring their distances. Webb allows astronomers to map how galaxies are distributed across vast regions of space. These maps reveal galaxies tracing long strands across the universe, gathering into clusters at intersections, and leaving behind enormous voids where very few galaxies exist. In other words, the cosmic web is not just a theoretical concept. It is an observed structure. Even more remarkable is the way matter appears to flow along these filaments. Gas and smaller galaxies move gradually along these cosmic pathways, feeding larger galaxies and clusters over time. Galaxies are not isolated islands drifting randomly through space. They are not isolated systems drifting on their own, but parts of a much larger gravitational network. Our own galaxy exists within this structure. The Milky Way belongs to a small group of galaxies, which itself is embedded within a much larger filament of the cosmic web. Over vast stretches of time, gravity continues to guide the motion of galaxies along these pathways, slowly reshaping the universe on the largest scales. And yet, despite decades of study, the true nature of dark matter remains unknown. Scientists have proposed many possible explanations. Some suggest it may consist of undiscovered particles that interact only very weakly with ordinary matter. Others consider the possibility that it points toward entirely new physics beyond what current theories can describe. Around the world, experiments continue searching for direct evidence of these particles. While telescopes observe their gravitational influence across the cosmos, so far, however, dark matter has never been detected directly. Despite this, its presence is extremely difficult to dismiss. If it were removed from our models, the universe as we see it would no longer make sense. Galaxies would not hold together. Clusters would fall apart. And the vast structures spanning the cosmos would never have formed. Dark matter acts as the underlying framework upon which the visible universe is built. At the same time, dark energy continues to stretch space on the largest scales, gradually pushing galaxies farther apart. The universe, then, exists in a kind of balance between two unseen influences. One draws matter together, building structure through gravity, while the other drives expansion across immense distances. Together, they shape everything we observe. The stars, galaxy, and glowing clouds captured by telescopes like Webb are only the visible surface of a much deeper reality. Beneath that surface lies an unseen architecture, guiding the formation of structure across billions of years. And even this vast interconnected universe represents only the portion we are able to observe from our limited position in space and time. Beyond the cosmic horizon, the universe almost certainly continues, filled with galaxies and structures shaped by the same invisible forces. The James Webb Space Telescope has not revealed an edge to the universe. Instead, it has pointed us towards something far more profound. The deeper we look into the cosmos, the more it suggests that what we can see is only a small part of a much larger reality.